very rarely ever do we know what sigma is and not know our mu. So in all these problems, we're trying to figure out what mu is. And so it's really unrealistic to ever know sigma, because why would you know sigma and not know mu? So instead, we're going to use S instead, because remember, mu is my population mean. Do you guys remember that one? So if mu is my population mean, and I don't know mu, what do I use instead to substitute for mu, or to my best guess at mu? In other words, if I don't know what the population height is, what's my best guess at the population height? I take a sample and use that, the average of that. So I'd use X bar. So if I don't know what sigma is, my population standard deviation, instead, what should I use instead? Anybody? Yeah, exactly, S. My sample standard deviation, right? Because they're both standard deviations, just I don't know the one for the population, so I'm going to use the one from the sample. The problem is it's going to be off a little bit. So because it's going to be off a little bit, then I need to use, instead of using the Z table, I'm going to use the T table, which is a little bit larger. We'll see more about that in just a couple of slides, to adjust for the fact that my S is off. And then don't forget, because of central limit theorem, you guys remember central limit theorem, our standard deviation is really equal to, I don't know if you guys remember, but it's equal to S over square root of n. Well, actually it was sigma over square root of n. But in this case, it'll be S over square root of n. So this is really what a standard deviation is in this case. All right, let's take a look at this T distribution thing. So this is our T table, T distribution. Yours looks like this over here. And the, oops, I didn't want that. Okay. So on the top, you'll see the confidence interval options, and then if it's two-tailed or one-tailed test, which we'll get into later on. But you're going to figure out, this tells you which row to use. I want a 95% confidence interval, so I'm going to use this column. Then I need to figure out my degrees of freedom. Degrees of freedom are equal to n minus 1. So whatever my n is, I subtract 1, that's my degrees of freedom, because I have one variable. So degrees of freedom, change this to red. Degrees of freedom is equal to n minus 1. You need to know that. It's going to come up over and over again. So here, if my sample size is 22, what's my degrees of freedom? 22 minus 1, 21. So I'm going to go down this column here until I get to 21. That's my row. Slide out to the correct column, and then here's my t-score, 2.080. That's my critical value. So I want you guys to go ahead and on your notes, go ahead and find these. Oh, you already did this. This is from your notes from last class. Find these critical values. You should have found them already. But go ahead and take 2 minutes and find them now if you didn't. Or maybe just 1 minute, and we'll go over that. If you need a t-table, there is one right here. You can use that. So this is our 95% confidence interval. Okay, let's go ahead and come back. Oops, I'm muted. Okay, let's go ahead and come back. So this first one, when n is 2, what's my degrees of freedom?
4.303?
No. So my degrees of freedom is equal to
12.706?
Yeah, hold on a second. Degrees of freedom is n minus 1. So if my n is 2, my degrees of freedom would be 1. Do you guys kind of follow me? So that's why we're doing this. You guys kind of remember. So when n is 1, then my Degrees of freedom is 1. Sorry, my n is 2. My degrees of freedom is 1. It's going to be right here. 12.703. 12.706. And then what happens when n is 11? What's my degrees of freedom? It equals 11 minus 1, right? So it's 10. Perfect. So when my degrees of freedom is 10, then we're going to go over here, and we'll see, oh, here's degrees of freedom 10. 2.228. Exactly. 2.228. Good. Now over here, we're going to have degrees of freedom equaling 60, right, n minus 1. So I'm going to slide down here. Oops, that wasn't on your sheet. If you scroll down, you'll see it 60, 2.00. 2.000. And then for 121, my degrees of freedom would be 120. Looks like 1.980. Yeah. 1.980. So the cool thing is, you'll notice, what was my z-score from my 7.1 notes? It was 1.96. And the great thing is, if you guys look at the very bottom row of your t-table, I don't show it here, but it's infinity. It's 1.96 right down here, if you have a t-table of your own. Mine, like I said, mine cut off. Maybe I can get it up here. You guys see it? Here it is, right here, 1.96. Because this bottom row is your z-table. So the beauty of it is, if you have this t-table, you no longer need this part here, because this information here is the bottom row of this table down here. It's right in here. So you don't even need that. So instead, you're just going to need, all you need is your t-table. And you can totally use the t-table on the test. You really need those on the test, so you're all good. The other thing I really want you guys to notice is, look, when my n is 2, I've only sampled 2 items, then my standard deviation is going to be pretty much crap, right? So I need to have a really big t-score to make up for that. But as my n gets bigger, n is 11, my t-score becomes a lot smaller, closer to the 1.96, because this starts, my S, my sample standard deviation starts becoming better. So here, my standard deviation, my S, is not very good. Here, my S is better. Here, my S starts getting much closer to what it should be. So I only need a t-score of 2.00. So as my n gets larger, which means that my S becomes closer to sigma, then my t-score becomes closer and closer to my z-score. So that's kind of the nice thing. As my n gets bigger, my S gets better. And as my S gets better, my t-scores drop until they end up being right down to what the z-score is, which would be a perfect, you know, if my S was perfect, then I'd have a z-score of 1.96. So that's kind of what I want you guys to realize and get out of that. So again, this is not unusual. It's very similar to the previous margin of error we did for proportions. Your margin of error is equal to your critical value times your standard deviation. The difference is our standard deviation is much simpler here. It's just S over square root of n. And our critical value is from the t-table, not the z-table, with n minus 1 degrees of freedom. So, looking at this one, we then find our actual confidence interval by taking our x bar and subtracting and adding our error. So our lower limit would be x bar minus our error, and our upper limit would be x bar plus our error. You can either write it this way with parentheses and a comma in between, or you can do it this way where you have the lower and upper limits and you're saying that mu is between them. It's greater than this one and less than that one. So you can write it either way. Here are the steps. let's get a reader to kind of go through the steps. Gina, can you go ahead and read this for us?
The procedure for constructing a confidence interval for mean with sigma not known. 1, verify that the sample is either normally distributed or n is greater than or equal to 30. 2, using n-1 degrees of freedom, use the t-table to find the critical value CV for the desired confidence level. 3, evaluate the margin of error E equals CV, critical value times standard deviation times S over square root n. 4, find the values of x bar minus E and x bar plus E. Substitute those values in the general format for the confidence interval. X bar minus E is less than mu, which is less than x bar plus E. 5, round the resulting confidence interval limits to 366.
Perfect. So it's really not as daunting as that. It's just find your, it's just, oh, where'd I go? It's just, find your critical value, find your margin of error, and then find your lower and upper limits, and then round them to 366. So this is your problem you had here, which Adam is going to share for us. So Adam, I'm going to stop share, and you're going to hit the new share, or you're going to hit the share on yours. So can you share your screen at the bottom? Adam, there we go. Oh, there we go. Okay. Oh, you don't have it on your screen. I'm sorry. You don't need to share your screen. I'm sorry. Just hold it up, and we can just hold up your piece of paper, and we can see it there. That's probably better. So hit the stop share, which is in the upper top corner. Yep. And we're gonna put you on the main screen. So speak.
Can you hear me good, Ralph?
Yeah, there you are. Awesome. So hold that up.
So this is number 2. Sorry, my handwriting's not that good. I'll go through it right now. So I started off with our n, which I said was 14. Our degrees of freedom, it's n-1, like you said, so I said 13.
Good.
X bar, I said was 33.2. And the S is 8.3.
Great. Hold that still for just a minute so people can take a look at it.
Okay. If they can't read it, I'll be happy to say it again.
Perfect. Great. And then,
yeah.
And then he did, see how he found his critical value? He looked it up on the table. Looks like
Yes,
he got.
I looked up on the T-table. Yes, I looked up T-table at 13 for 95%, and I got 2.160 for my critical value.
Great.
Right there. And I calculated that in to get E. I said E equals 2.160 times the upper value, which is 8.3 standard deviation, divided by the square root of n, which was 14. My answer for that one was, I ran it to four places. I got 4.7915.
Perfect.
I rounded those. And then I took my X bar, which is 33.2, and I said plus or minus the 4.7915. And I got, for the lower portion, I rounded 2 places. The lower portion I got 28.41, and the upper I got, sorry, was that?
Yeah, you did.
That one?
Yep. Awesome. Perfect.
Okay.
Thank you.
Well.
So, excellent. There you go. Let me share my screen again. Good. So that's the answer for that one. Terrific. Thank you. And then we're going to move on to this one over here. This one's fairly straightforward. Again, this is exactly the same as it was for proportions. So if you have a confidence interval, so in our case we had, what would we have? We had, it was like 28.4 to was it 38 or something like that? 0.0, something like that. I don't know. It doesn't matter. Again, remember that this is our x bar in the middle, and then we have our. What we're doing is we've added our error to that, and we've subtracted our error to get to this, and so these are our lower and upper limits. So if we wanted to know x bar smack dab in the middle of them. So if I want to know what my x bar was, all I have to do is average these two, right? Add them up, divide by 2, and that would give me my x bar. And the other thing we know is that from here to here, this is an error. This is another error. So from here to here, that's I jump e, I jump another e, so it's 2e to get from this lower limit to this upper limit. So if I subtract them and divide by 2, then I get what an error is, because this is from this distance from here to here is 2e, right? Because this is an e, and this is another e. Okay, so that's again just a refresher of what we did with proportions. It's exactly the same. It doesn't change at all. And then this is just a quick summary of what we've gone over. So here, again, remember, we're not going to even deal with the idea of when we know what sigma is, because we never know what sigma is if we don't know what mu is. But we do know these two things. So here's a couple things. So the first one is if it's a mean. So here, if we're talking about means, then I'm looking at something that is an x bar. I have an x bar. I'm trying to estimate a mu, and I use the t distribution. Because remember, we're using s here. So that means you have to estimate. So the easy way to remember that is to think of mean Mr. T. So Mr. T does not look, he's not mean, but he looks mean, right? So if you kind of think of mean-looking Mr. T, it'll help you remember, it's a mnemonic for remembering that mean goes with T's. So mean Mr. T means use a T distribution, T table. The other thing you've got is you have proportions. So if I've got a proportion, then I'm going to have a p hat. It's my sample proportion. I'm trying to find p naught, or p, since we call it just plain p. Those use a z distribution. And one of my students said the way that he remembers it, he says, just think of easy peasy. Right? That's something we all, easy peasy, everyone's heard of that. Because when you have a proportion, a p, then use a z distribution. So p uses a z distribution. So that's kind of an easy way to just remember it. Means use a t distribution, mean Mr. T, easy peasy. So everyone just take 10 seconds on your own and say it to yourselves. Mean Mr. T, easy peasy. Go ahead, say it. And I think for now we're going to take a 10-minute break. So go ahead and take a break, and we'll come back at 8:44.